So Andrew Morozov, who is going to give us a very interesting talk about it.
Thank you very much, Sergey, and thank you for coming this afternoon to listen to this talk. And I should, as kind of warning, I should say that in my talk I didn't include too many equations, so at least as compared to the previous talk. So this will be a conceptual talk, and my idea is to combine several other talks and to try to connect them and to see where we are in terms of tipping. So, and first of all, this is a joint work with Alan Hastings and Sergey Petrovsky and Valerio Luccherini, and all of them are sitting, present. And my talk will be about the diversity of tipping points. And as a kind of simple example we can think, so from a nice state like this one, if you think that after 1 month of this very intensive program we might be like that, hopefully not, but as an example of tipping.
Nice humor.
No, it wasn't good. I was serious. Okay, no. No. Okay, let's be now serious at the moment. And well, I try to find some rigorous or close to rigorous definition of a tipping point, and what I found was in this book or maybe a report by Tim Lenton and others, and that report included 200 researchers on tipping point, and they define a tipping point. I don't want to read it, but something as you make changes to the system, and the system responds in some amplified, substantial, widespread way, and this impact is often irreversible. And definitely through previous talks we came across several types of tipping, and the central one is the so-called B-tipping, which is bifurcation induced or bifurcation based tipping. And in this case you have classical example bistability, and for instance so this is stable branch, unstable, and zero stable, and we're on this branch initially and we change parameter, and at some point we have a pseudo-node bifurcation, and then we just fall to the extinction state. And well, this is on the right hand side you can see the same thing, but explained based on the potential. And the question is, I don't want to talk too much about this type of bifurcation, and the question is about other possible scenarios of tipping. So of course I shouldn't ask this audience whether or not other scenarios of tipping exist. Of course we already learned about R tipping or N tipping, but whether or not we can go beyond those well-known scenarios. So the talk will be about diversity of tipping phenomena. And by the way, recently I talked to one of my colleagues, and I said, I'm currently working on classification of tipping points, and that person just said, tipping points it's very simple, it's just this kind of S-shaped curve, and kind of that's it, the science is kind of stop here. And unfortunately this is kind of a very typical impression of many people, so, and they think that this is all so the start and the end of tipping theory. And at the end of my talk hopefully I'll convince you that it's not that simple, of course you know, but yeah. So very briefly, well, when in my presentation I'll the models will be ecosystem models, but of course the ideas will go beyond just ecosystem models, but this will be centered at ecosystems or ecosystem models. And very briefly I would like to list few, not all of them, but few important features, well, which actually define uniqueness of ecosystems as complex systems. Important thing is well, about the complexity of ecosystems. For instance, if you consider this food web, quite complicated food web, so it's described by this network, and definitely the model of this network tipping there should be complicated. Also, broadness of relevant spatial scales. You can think about microorganisms, and from, say, microbes to big mammals like elephants and whales. So the sizes are different. It's not just about the sizes, but also about their home ranges, about their dispersal. Definitely you have quite broad range of spatial scales, so maybe within the same ecosystem. And also in terms of dynamics, this can be quite complex, as you can see from some experiments. It can be cyclic, chaotic, or with some noise. So quite complicated dynamics. Multiplicity of temporal scales. So for algae and zooplankton, fish, bird, and different generation times, and we need to include this into our models. Spatial complexity, so ecosystems they are not homogeneous in space. Also, some species have active feedback on the environment, like those ecosystem engineers, like beavers or ants. And also, the question is about phenotypic plasticity, and because living organisms and ecosystems can change. Well, they have a physiological response. They can change their physiology. And honestly, just by chance, this morning I included this example with butterflies, and well, and I didn't know that Christine also would be talking about insects and phenotypic plasticity. So these are important things, definitely, for the ecosystem. Okay, and let's go to the classification which we developed based on the existing literature, so all together with my co-authors. So it's, well, firstly, we can start with R-tipping, and actually, I probably will skip this slide. You already understand the idea of R-tipping. So you have a system which is non-autonomous system, and some parameter is changed, and the question is whether or not you'll have any qualitative or quantitative changes if the rate of change in the system, well, you vary this rate. And actually, Sebastian nicely introduced to us the theory of, partly the theory of R-tipping, and in particular, so it was mentioned that most of theory was related to the so-called asymptotically constant forcing. So this is time, this is forcing. So after some oscillations, you start from something constant and you go. And it can be instead of constant things, it can be so it's not, it's constant. Sorry, so constant. And all theory, most of theory, as far as I understand, is developed to this case. And the idea was to find the some critical value of change R such that we have tipping in our model. And together with my colleagues, and in particular with Karen. Oh, okay, yeah. So we tried to find altogether to, well, produce this nice table to find some examples in ecosystems of R-tipping of different scenarios. And if you are interested in advertising our work, if you're interested to find some particular study cases, well, with some different scenarios of R-tipping, you're welcome to look at this paper. And recently, by the way, I came across that paper on R-tipping, and in that paper, the authors actually tried to produce some really, as I say, rigorous definition of R-tipping, kind of generalized definition of R-tipping, and well, as compared to the previous case. So they also considered cases where you can have so this situation where the increase or decrease is unlimited of some parameter. Anyway, and their definition, they claimed that the definition was the most kind of rigorous one, and this was both based on the pullback attractor, and they said that, okay, initially, so before tipping, this pullback attractor is forward attracting, and then if after changes in the system parameters, this pullback attractor loses its forward attraction. In this case, we have R-tipping. So it's kind of a generalization of the previous definition. And as an example, so you can see this equation. This can be a population dynamics equation or just any abstract equation. And in this equation, so it's relatively simple non-autonomous system, because so you can easily replace x minus rt with some new variable y, and from non-autonomous system you can go to an autonomous system, and then in that system you can check bifurcations, and this is an example how it happens before tipping. So the trajectory follows of one of this pullback attractor, which is just a straight line, and after tipping, if the up above the critical rate, so you have a bifurcation, and you simply don't have this pullback attractor. And I just thought that it would be the most general definition ever, but actually maybe Sebastian will where is him? Yeah, here you can correct it, because in this case, for excitable systems, probably this might not work, right? Because still we have in this case the pullback attractor is still attracting, right? And this some kind of generic definition is not generic. No. Yeah. So my point is to say that it's hard to provide to list the most possible generic definition, and different scenarios are possible. Yeah. So, and my point is it's far from being set. Okay. And for instance, we can also consider some realistic scenarios, not only asymptotic constant, but also asymptotically periodic things, and also we still need develop some methods to deal with this kind of situation. Okay, so in my talk I'll provide more like classification rather than describing methods how to deal with those different scenarios. So n-tipping, and n-tipping was mentioned, so noise induced tipping was mentioned many times. So in the simplest scenario, you have, again, this famous S-shaped curve, and then you stable, unstable, unstable states, and then you impose some noise. It can be big noise, it can be small noise, and then you have transition. So before this critical point, so you have switch between the two branches, and this is an example of noise-induced tipping, but they can be more complicated examples. Also, well, we'll continue our classification. So the so-called S-tipping or shock tipping. Again, the famous curve. And now, instead of instead of having noise, so we have a shock. So just maybe one single shock, and from here we go to the basin of attraction of the lower stable equilibrium, and well, we have a tipping point. Also, we have a combination of the previous tipping scenarios, which we can call AN tipping. So this means that this is we have noise in the system, but in this case, a noise is non-Gaussian and anomalous. For instance, like Levy type of noise, and well, so in this paper, so it's by Marisa and I know Professor. Yeah. Both co-authors are here of this paper, and it was shown that this kind of non-Gaussian noise can produce tipping, and it's important to separate this scenario from the standard N tipping, as we believe. Okay, let's proceed in terms of our terminology. Phase tipping or P tipping. So there will be, if I'm not mistaken, will be a lecture tomorrow morning, right? Partially on P tipping. So if you're interested more, so I definitely recommend. I advertise someone else talks as well. So the idea is briefly. So for instance, this was initially proposed by in this paper by Hassan and Sebastian and Rebecca Tyson, and they considered a predator-prey model. And by the way, this graph is not necessary from your paper, but the idea is the same. You have, say, a limit cycle, and then a limits a predator-prey model, and then so you impose. So you change your parameters. You can be some carrying capacity. I didn't include the change of parameters, but some of parameters should depend on time. And you switch. Well, you increase. You start increasing your parameter at some point, and the result of such variation parameter will strongly depend where you are on this limit cycle. So, and you can even introduce the probability of tipping. And you can also think about more complicated models like food web models with chaotic attractors. And for those models, you can also introduce the probabilities to tip starting at some point. So sometimes you can, in here, you can tip or you don't tip. So it's, well, it's now probabilistic. So it's a recently new scenario of tipping. And also it was mentioned earlier today in the talk by Alan, right? Another scenario is about long transients. So in this case, there are a few examples of long transients in ecosystem models or just in dynamical systems. The idea is you have some meta states, so you don't really change any model parameters. But for instance, if you consider some times, some time windows from say 500 until 3000, and you cut that bit, you might think that as an observer that nothing would never change, right? But almost suddenly you have a transition. You can call it tipping, but interestingly, so it's a particular case of tipping where the change of parameters is just zero. So it's a particular case, right? So nothing happens, but still you have the same similar pattern which you observe, and it's tipping. Okay, so the paper where we emphasized the importance of long transients. And also in the rest of my talk, I would like to speak a little bit about tipping cascades, because it's a quite hot topic nowadays, and I realize that still not much is known about tipping cascades. And well, people normally talk about classical domino effect that, for instance, you have domino pieces and you push one piece and all pieces will eventually fall. And you can consider, well, say, this, it's a similar thing, but at the scale of the planet, and you have different ecosystems, Amazon rainforest, and well, AMOC and other things. And the idea is everything in this world is connected to everything. And if you, well, you have tipping in one system, so it'll be eventually like a domino effect. And then I thought about, well, the domino effect. I thought, it's probably even kind of little kids understand the idea of the domino effect. Is it as simple as this? And I realized, of course, we realized it's not that simple. But before we proceed, I was a little bit amazed to see the risk calculated of the domino effect. You see, it's like 31%. It's not 30, it's not 40, it's very precise. Well, maybe I'm not criticizing, but maybe it's very accurate, very accurate. No. We need accuracy, but yeah. Okay. So before going to our classification, so myself, I have a big question about what we can understand by tipping cascades at all. For instance, in food web. So if we have this food web of different species, so many, I don't know how many species, and the idea is if we remove, say, some of them, and after that the whole ecosystem collapses, the whole food web collapses, is it going to be a tipping cascade or something different? Because, well, it will a lot depends on the definition. Because if you think about some dynamical system and you remove some important part from the dynamical system, or you have a car, you remove wheels and say, oh, the car can't really, because that's kind of domino effect. In a certain sense, yes, but do we want something like not completely trivial, but more complicated scenarios, as just removing some essential part from the system and being surprised, nothing works. Yes, so in particular, so we found interesting examples in the literature. So, as I mentioned, ecosystems are spatially heterogeneous, and while tipping cascades can propagate across space. And before talking about the systems, the scenarios, I just briefly introduce to you, master-slave systems or systems with bidirectional connections. So mostly I will talk about master-slave or driver-driven system. You have system A, say in space, B and C and D. So system A affects system B, but system B doesn't affect system A, and system B affects system C, and so on. And a lot in terms of classification, surprisingly, can be based on this system. But in principle, this can be bidirectional connections. Also can be network. So, but many things can be derived from this simplified system. And in our review paper, we did classification of the existing tipping cascades. I'll briefly provide we'll talk about most of the scenarios. And the first one is multi-phase tipping cascade. So you have this master-slave system, and you change your system parameter from large to small, well, small to large, doesn't matter. And suppose for simplicity that this subsystem by itself is characterized by bistable. Again, the famous S-shaped curve. So you can't really avoid this curve, at least to start with. Yeah. So that is, you change parameter, and then so you have this switch to a different to a different state. We have tipping in system A, but you don't have tipping in other systems. And importantly, so to separate this from the domino effect, the important requirement is if we just stop here, those systems will stay in their previous state. So one by one, so by increasing this parameter, so those system will gradually switch to a different to a different state. So, but when you stop, the rest of the system will stop switching. So, but we might have before going to the different type of tipping, so just to see what we can observe as external observers. So you have time, you have population densities, for instance, and you have one, so A, B, and C system. They switch to the alternative state. And what about the next similar but different type of tipping, indirect tipping? So imagine the situation where you initially, so you change your parameter, and you say you don't have any tipping in system A, but you have tipping in system B, and you don't have tipping in systems A, C, and D. And then you keep changing your parameter, and still you don't have tipping in system A, but you have, you're tipping, like it's spreading across the entire system. And again, you keep increasing your parameter, nothing happens. So, and eventually this system tips. So you may have a situation where the system, and basically the parameter you change is not across the parameter you change only in system A, importantly. I didn't tell you, but only in system A. So not in other systems. In principle, you can change everything, but for simplicity, just in the first system. So you have indirect tipping. So the first system doesn't tip, but all the others would tip. So hopping cascade phenomena. So suppose you do, change parameters in system A, and you have tipping in system A, but not tipping in system B. But, through this chain, you have still a propagation of tipping. So you have tipping in system C. So you have this phenomena of hopping cascades. And then you keep changing your parameter, and system D tips, but still system B doesn't. And eventually, finally, you have everyone tipped. So this kind of pattern. And also, finally, so I started with the domino cascading, and so in this short part of classification, it will be the final one. Domino cascading. So it's, the idea is simple. So in this case, you may not even change the parameter. You just do your shock tipping, and tip system A, and then you just wait what happens. At the moment, this tipping doesn't really propagate, but at some time, so because this is we'll talk about why we have this delay. So we have tipping in system B, and then tipping in system C and D. And again, we have more or less the same situation. And importantly, when you talk about a domino effect, so importantly, we need to have this kind of periods of time when system A tips and system B doesn't. It's important. So we have some kind of a relatively some substantial amount of time when you can say, this tipped system, well, the first system tipped, but the others just wait. And eventually they go one by one, but after each tipping, we still should have, according to this scenario, domino or slow domino cascading some time. Eventually they'll all tip. And it's probably not very nice example, but if you think, you should not think too much about this, but headless chicken, right? You cut. But I'm vegetarian, and I'm vegetarian, but the chicken can still run within some time. So, and this is an example of the domino effect. And yeah, we need to have some time. One. I'm just describing how other people are cruel. Okay. So we should avoid this. Yeah, so how we should do, basically, how we can modify this. The solution is, for this chicken, is join cascading or fast cascading. And you can see, after we actually, well, we tipped our system, so by shock tipping, for instance, so almost immediately all other systems, subsystems. So in this case, we just cut the head, and it's okay. Let's return to the ecosystems. So what we see here? So it's almost immediate, well, cascading, and it's important to separate between this slow domino effect and this fast cascading. And mathematically, so it's not just, mathematically we can introduce some definition, some rigorous definition. It hasn't been introduced, such a definition hasn't been introduced yet, but we can introduce this kind of definition for slow domino cascading. For instance, we can, according to the definition, we can require that those times, well, for some parameters, can be made infinitely large. And the question is, why do we have these breaks between next tipping? And in many cases, it's because of transients, like ghost attractors, for instance. And a system is in the ghost attractor, and only after the system, and then you have tipping in a different system. You can add noise and also check how noise affects this tipping. And the final one in this classification is what we call quasi-cascading. And actually, it's not really even cascading at all. But imagine a system of almost individual subsystems. And then you impose time, but the parameter, some parameter which is included in each of those subsystems also changes, and this can be due to some noise. And one by one, so I put those crosses, meaning that maybe they're linked to each other, but the coupling is weak, right? And when they are almost independently, they tip. So, and in this case, so you also have an impression that you have tipping. And this is a problem, by the way, I'll skip this slide. The problem is, when as an external observer, you observe the subsystems, and you have this kind of dynamics. And you might think, at the moment, don't really look at the parameter variation, just at the variation of the densities. And you can think, what kind of tipping cascades do we have? It's probably the domino effect, maybe. Or maybe this is, you say, an indirect, it's a multi-phase tipping where one system tips after the other one, but tipping in one system doesn't really signify the tipping in other system. Or this can be also quasi-tipping, and just looking at those patterns, well, by looking, we can't say anything. Or this can be, well, if we look at the parameters, 3 different scenarios are possible. It can be gradual modification of this parameter, or it can be just one shock, or it can be just noise. And the pattern observed will be very, very similar, undistinguishable. Also, for tipping cascades when they are fast, so still just from observation, sometimes it's hard to say what happened. Maybe it was just one impact, maybe it just also effect of noise, and maybe it was also a gradual increase. So, but for all 3 scenarios, we may observe similar pattern. Okay, so in terms of, well, I finished with classification, and what are the open questions related to tipping phenomena in ecosystems, but not only in ecosystems, also in, well, climate models, in general in physics. So the first question is, well, whether or not we missed any other interesting tipping scenarios, because as far as I remember, yesterday Chris Bard presented, well, kind of novel mechanism of tipping with non-smooth bifurcation. Whether or not it's a different mechanism, I don't know. But the question is whether or not other tipping scenarios exist. And by the way, would be interested if you are aware of something new. I will be interested in discussing with you. So the other thing is, so it's how we can define tipping. So, and initially, all tipping was related to the idea where we're currently in the beginning on some attractors, right? For instance, at the stable equilibrium, and also on any attractor. We're sitting on some attractors, and then we make some changes, and then we see whether or not we have tipping. And then I came across this paper by Ulrike, and in that paper, the tipping was defined in a slightly different way. It was defined, but the mechanism was slightly different. So the idea was that you have some model, 2 species model, so interacting species, competition between 2 species, and the parameters of the model, or one parameter, I don't remember, so was either increased, well, modified either in a fast way or slow way. Well, the initial conditions, by the way, were not necessarily, well, on attractors. And for instance, for fast change of parameters, so starting from different initial conditions, you can arrive at some final equilibrium points. So red dots signify, they denote equilibrium points after we have changed our model parameters. So that's the same. And here, the same situation, but with a slow change of parameters. And from the same initial conditions, you eventually can arrive at different equilibrium points. And initially, honestly, I thought that whether or not we can call this tipping point, right? But after some thinking, I thought maybe we should call it, but in this case, we should broaden our concept of tipping. So, and the question is still open, how we can define tipping. The problem is that if we broaden it too much, we can include like everything, and it will be not very it will be pointless, right? So it's still an open question, how can we define tipping? So beyond the classical definition. The other thing is, I didn't really mention that, but of course it's about early warning signals of tipping, and well, initial methods based on different things like autocorrelation functions and other things. So they kind of work, but if you have a more complicated scenario like domino tipping and other tipping cascades. So to me, to the best of my knowledge, we still need to derive reliable early warning signals. Whether it's possible at all for some complicated cases, I'm not sure. But let's not be pessimistic. And also, the other thing is, the other open question is, well, it's about shock tipping, but we can have the situation where we have multiple shock. It's from a different paper by Ulrike. So the idea is they considered single species model, and you have it's not mine. Yes. No, every time I give a talk, this is the first talk when okay, so it's the first talk without one call. Okay, so yeah, the idea is, well, initially the system is sitting at some stable equilibrium, good equilibrium, and with high species density, and then the parameter, the current capacity, is largely decreased. And you can see that, well, the system, well, almost collapses, and this is the boundary of the low equilibrium. So if you go beyond this boundary, so you'll go to the other state. So, but you see, after this big shock, still the system can survive. And then you can impose a slow and very small shock, and you kind of kill the system. And initially I was very much surprised, but now maybe I'm slightly less surprised, because you are still near the boundary, right, of the other attractor. And if you're near the boundary, even small impact, small shock can matter. But still, it's important to not to consider a single shock, but say multiple shocks, their amplitude, their length, configuration. Still an open problem how the system, our systems will resist to this. And also, importantly, so it's important to connect our models of tipping, predicting tipping, and real ecosystems, and check whether or not our models will work with S-shaped curves, and what we have what should we expect to find in real ecosystems. For instance, real ecosystems can be always in some transient regime, and maybe we will not have any tipping at all, or maybe we have some other tipping scenarios. And I just came across this paper, and I should say that this paper is kind of anti-tipping paper. So, and I was saying that the tipping, well, in this, in the normal set doesn't exist at all. And I was not surprised to see that that paper was cited only 60 times. It's kind of a lot, but not a lot. But at the same time, other anti-tipping. No. But no, it's a different story. But at the same time, tipping papers received thousands of citations. So because I think that I realized any tipping point person, nobody would cite this. So otherwise, it's like killing your own research. Yeah, but those guys, by the way, you know, say, no, it's kind of black magic. No, they still provide some points. So there is some confusion. Still, we need to rethink our definitions of thresholds. They're partly they're correct in something. So we should not ask, that doesn't exist. So, but we still need to better connect our models to reality. Okay, now conclusions. So I'm finishing off. So hopefully I convinced you that tipping scenarios in ecosystem models are very diverse. And again, if you come with your own, as you think, scenario of tipping, we'll be very happy to discuss this. So we're quite lucky we're living in good times where the tipping theory is being built. So it's growing. So it's new science. So it's not just S-shaped curve, okay? And well, of course, now you know. And the classical concept of tipping in terms of, even in terms of definition, in my opinion, should be revised and, well, to be more modern, to correspond to the more realistic situation. So, to my opinion, still we need rigorous mathematical theory of cascading phenomena, and well, connection to connection between models and real systems. I also didn't say anything about this, but importantly, it's important to check possible tipping avoidance in ecological systems like phenotypic plasticity, spatial heterogeneity, and others. So, in her talk, Christina actually explained us that phenotypic plasticity in her model actually facilitated, right, tipping, but can be some different scenarios where the system can avoid tipping, and definitely this also needs to be analyzed. And yeah, I think I'm done, and thanks a lot for listening.
Yes, I wanted to, on the last paper, you should just a comment. Thanks, Andrei, for this summary. So, a comment on this paper, because of course there are few, let's say, problematic aspects. So this paper proposes this, what is called a paralogism. So it makes a logically wrong argument, saying tipping points are described as R one-dimensional saddle node bifurcations. Since a lot of phenomenology does not agree with this specific model, so tipping points don't exist. So this is the logic of this paper, okay? So it's extremely problematic, and the argument is, since this problem does not fulfill with this specific model, it does not exist, and it's a waste of time, because the title is extremely aggressive. It says that addressing tipping points confuses climate action. Now, the slight surreal aspect is that the first author of this paper is my colleague in the chapter 8 of the IPCC report on tipping points. And asked, so, you know, I try to address the issue. So, like, if you say this, because if you read this paper, giving a short summary, it says, people who do tipping points are scientific imposters, and the whole topic is bullshit. This is what it says.
So he's confused.
No. Believe me, there are serious issues there. But what is surreal is that then, in the communal discussion on tipping points, I try to say, okay, what about this paper? And the answer is silence. So what I believe is that this paper is a ballon d'essai to create noise. Okay. And it fulfills also some scopes, scientific, political scopes I don't understand. But it's a very interesting reading. I needed days to read it because I would be very angry. Not because, I mean, there are many papers I disagree with, but they can be extremely good papers, and I'm happy to be wrong. But this is, I think, a good reading, especially for early career researcher, to see how you should never write a paper. It's an example of intellectual dishonesty, and it's really bad. Everyone writes wrong paper. I mean, I'm the first, but the problem is that I think it has a goal. It's an undeclared goal, and I really don't understand, because some of the authors are very, very distinguished scientists. I never understood the logic of this. It's quite scary, actually, because also it came out exactly in the right moment when the IPCC process was starting. And I don't understand. There is a lot of strange things happening on the side of IPCC. Very strange things. Yes.
From outside, I think there's something else that's also extremely problematic in this. You just read it here. It says, here we critique, blah, 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 for conveying urgency without fostering meaningful basis for climate action. What they're saying is, if you find something scientifically, do not report it if you cannot give a solution. And that is mixing science with political action. And that is extremely dangerous. We should never We might be wrong, we might be
Yeah, of
make
course.
bad papers, etc. But what we find, we should report. We should
Absolutely.
never ever have political
Absolutely.
motives for whatever we report in scientific.
You're right. The paper says if it's not actionable, is not science that deserves to be reported. This is scientific censorship of the worst kind, because who decides what is actionable? Yeah, but it's. I mean, of course, you.
But you could just point it to imagine this was in medical sciences. We
Yes.
have discovered this big disease or this big don't smoke, you get very sick. Oh, but if you don't have a solution to whatever, don't report it.
No, but
So it's actually what they're saying.
no,
It's really
true.
dangerous.
Yeah, but I'm not advertising this. I want to bring to your attention.
Oh, about this. This is good to know that exists.
Questions. Let's
Yeah.
let's proceed to other people to also have questions, please.
Yes, Valerio, I completely agree with you.
Mm.
But on the other hand, we should say that we have serious problems with the use of tipping points.
Yeah, sure. Yeah,
In the scientific community.
absolutely.
And some people that use tipping points, they also do that for political purposes, which are not explicit. So we should address this
No,
also.
yeah, yes. I think the only good, the idea is if one says the expression tipping points has been watered down to include a large variety of phenomena just to use the brand tipping point to get scientific attention, this is absolutely right. And I think this is scientifically a negative development. So this I agree. But and there are examples, of this which I've discussed. But from this saying that the whole notion is wrong, and it's wrong because since people use it in a confused way, there is no action you can take. I mean, it's just putting together, mumbling together words and concepts. But no, what you say, Fred, is totally right. It has been used also in ways that are wrong. I mean, and the classification, I think, Andrea is proposing and many others are proposing, is essential to diversify the phenomena, still trying to give an overarching picture. And it's a very difficult exercise, I believe, here. No, you're right.
Can I make a comment on the more scientific part?
Not necessarily on this, but yeah, on other parts. Yeah.
Regarding the cascading effects.
Yeah.
So I think it's very important to have the timescales into account. It's not very difficult to imagine systems where you have this delay between the cascading effect. You could just think about the melting of the ice sheets, and that can cause the AMOC to collapse. And the AMOC might even collapse before we even see the collapse, because it's just the freshwater input and it has not reached the level yet. But what I think is a little missing in what you told is the timescale of the change. So when we have early warning signals, we call them early warning signals because they're early warning signals. So they are in time before it happens. But of course, if the forcing is changing so fast, and I'm not talking about rate induced tipping, I'm just talking about the usual B tipping. If it happens too fast, you don't have time to discover the early warning signal, even if they're there. And if you have cascading, you can just think about it, the buckets that fall with water. So you have the first one, and you will see no early warning signals in the others. Of course you will not, because they have no forcing. And then this one tips, and then they have the forcing that say push, and then it goes out. You will not have time to see any early warning signals. So it's not rare that you don't see them in the next ones. I would not expect there would be time to see early warning signals. It's just going like this towards the cliff, and then it says poof, and then it goes over. If you have these cascading effects where one tipping is actually causing the next tipping. And that comes to the next thing, the usual thing we say in statistics, correlation does not imply causation. And of course, you can have tipping in several systems more or less in the same time, and they have nothing to do with one another because they're all caused by the same, say, global warming or whatever. So they have the same underlying cause, but they have nothing to do with one another. And there we just have to be clever and try to understand and include the physics. And there are also sophisticated ways of doing statistics for figuring out if they're causing or not. It's just very difficult for me to see that can be done in climate because we don't only have one realization.
Yeah, I fully agree. But you can also think about things like hopping cascading, right? Because probably based on already your what you observed, you think, definitely you'll be the next one, but nothing happens.
Yeah,
And
it could be. I mean, if you believe in that, something happens in system B that system C feels. If that is not, your arrows are wrong. But it could be that tipping in that move system B a little bit that is enough for system C to tip. But of course, there must be something in system B, otherwise you need an arrow around it.
And sort of, you're mentioning, I thought you were going to say something else, which is
Sorry.
no.
I love not to be predictable.
That yeah, that's all. Is that here you're implying that we know which system affects which, and that's probably something which is really hard to know.
Yep.
And in some sense, you'd want to infer, and you might get this wrong. And that's one of the big unknowns. I mean, you should really be starting with what you really can observe, which, as you say, is the behavior perhaps of systems A, B, C, and D. And one interesting thing is what you can use then to infer what the actual, essentially, connections are. Yeah.
But I think that also depends on whether, say you want to know whether there is an arrow between system A and system B.
Yeah.
And that arrow can be in two ways. One, well, in many ways, but one way could be if system A tips, it goes to another state that makes system B discover it.
Yeah.
In that sense, you would never ever be able to detect anything before the tipping. But it could also be that small changes in system A make small changes in system B, and then you can actually detect that.
yeah, sorry, for interrupting, because I'm saying that changes even after tipping, changes in system A can still impose, because you have this links, right? Because system A doesn't really affect system C, it affects system B. So still there are some changes, but they're not they're not like, it's not tipping, but still. So system A causes tipping in system C. So and
what you also said would imply that all you can observe is system B. You may never see early warning signs.
yeah, maybe far away from tipping can be still far away. Still something changes, parameter changes, and this highly affects C. But in system B itself, you're still far away from tipping.
Yeah, also about the early warning, I think it's this. So if somehow we can separate our system in several subsystems, like here, it also tells you that early warning needs to be targeted to observable of a specific system, because of course, if you have anyway, just maybe even a shift in A that does not lead to tipping, but this sort of drift might cause a tipping in another system like B. So in which case, if you look at A, nothing specific is going to happen, but if you look at B, you're going to have an early warning. So somehow there is often when people look at early warning, they take sometimes serious and they expect that everything will be observable there. If we have this sort of categorization into different subsystems, things are not necessarily true. So that finding an optimal early warning is clearly essential in this case. And I mean, there is also a paper by Johannes Lohmann who tries to understand how to define. I think Fred is also involved, in fact, and tries to define what is the optimal way to define an early warning that sort of sees the proximity of the state to the unstable solution. Yeah.
Okay, yeah, absolutely agree. I can also add that it can be also hopping not just through a single system, but through two systems, and also in this case, definitely it's a linear chain, right? But it can be some complicated network, and in the case, you easily check, oh, what system A, what system, but because they're okay, you can use. Masters, yeah, but when everything is like a network, it's hard to say. Oh, from the point of view of system D, so where should I expect some danger to come, right? Yeah.
Because it might have tipped, but it's so slowly going to the tipping, but it might still affect the others. We
Yes.
do not see the system as already tipped.
There
Yeah.
has been a paper recently, I think it's still on archive, published, written by a couple of people from Exeter. I think Tim Lenton is one of the authors that is particularly focused on importance of time scale of the subsystems. So that's exactly your point here. So I can send you read if you're interested.
Yeah.
Yeah, just changing a little bit of topic because you mentioned also the asymptotically non-autonomous case. So I want to, since we advertise a bit of bad research, shamelessly advertise my research because there's a bunch of papers on the asymptotically non-autonomous case, which I think it's worth mentioning, especially because, I mean, when it comes to climate, we know that time dependency acts on a variety of timescales, and so the relations between tipping and non-autonomous underlying forcing produces a variety of phenomena that don't exist in asymptotically autonomous systems. And so it's very important to study them because these are possibly dangerous scenarios that we're going to face. So including complexity like strange non-chaotic attractors, chaos in dimension one, even just in dimension one, which are things we don't see in autonomous systems, and so on and so forth. So
So a good point. Yeah, excellent.
Yeah.
That's why we are all here. Yeah.
Thank you. More questions? Okay, well, we still have a whole day tomorrow. If any later question comes out, we can still have time tomorrow. For the moment, let's thank speaker again.